The elephant trunk is a highly flexible and powerful biological structure in the world because it can completely interact with surroundings like grabbing, winding, and transporting their food. Elephants employ their trunks for more than just survival tasks. These gentle giants use their trunks for social interactions as well. In this work, we propose a novel aerial continuum manipulator that is inspired by the trunk, aerial elephant trunk, AET. AET is composed of a small quadrator and a triple-section continuum manipulator. The quadrator provides a flight platform in the air, and the continuum manipulator has the similar motion behaviors like the trunk, such as dexterous shape transformation. AET can transform to various shapes, which are extremely useful for working in complex environments. We build up a comprehensive closed-loop kinematic control architecture for the continuum manipulator by setting desired 6 DOF poses for the manipulator tip. The manipulator can be controlled to track the desired pose and showcases its real-time estimated shape. The effective 3-dimensional workspace with respect to the UAV frame enables the manipulator to execute various deformation motions. Even though there is an obstacle, for instance, we set the desired location and put a box in the path as an obstacle. The manipulator tip can avoid the box and find another way to reach the target point. Moreover, the pose control can be used to guide the tip to wrap objects. For example, the cylinder is put horizontally, and the manipulator is controlled to move around the surface of the cylinder until tightly wind the maximum area. Next, a bottle is put vertically, and the manipulator is controlled to move in a different direction to wind the bottle. Then, we validate our shape estimation algorithm. The shape is estimated in real time, and it closely aligns with that of the real AET, which changes to various shapes in the air. Next, we show that our AET can closely track desired trajectories during the flight. 4 different trajectories, level circle, level rectangle, vertical heart, and vertical 8, are designed for the UAV to follow in 3D space. Although we arbitrarily swing the continuum arm, the UAV can still track the desired trajectories in a satisfactory manner. With the shape deformation capability, we conduct that AET can grasp various types of objects by performing whole manipulation. The entire winding process is divided into 4 steps: approaching, winding, transporting, and dropping. AET approaches the horizontal pillar with a front-top bending shape. Then, instead of grasping it with a gripper, AET bends its whole body to an O shape to wind the pillar and successfully drop the pillar. Similarly, the winding of a vertical pillar is also performed by using the whole body manipulation of AET. Since the pillar could slide down during transportation, we employ a spiral shape to wind the pillar multiple circles to ensure firm grasping and prevent falling during transportation. The final case is the winding of a bench with an irregular shape. AET approaches the bench and wins its corner. By the closed-loop configuration control of the continuum arm, the bench will tilt to its center of gravity line to reach balance. Then, AET will transport it and drop it to the destination. Next, we demonstrate the capability of AET for aerial manipulation in narrow and constrained environments. We use a pipeline bent with L, C and S shapes to simulate different, constrained environments in which an aerial manipulator works. The pipeline is slender, radius is 6 centimeters, semi-closed, and has a specific shape, which is challenging for conventional rigid link aerial manipulators to navigate through. Based on the shapes of pipelines, we predefine the arm's configuration and execute the desired tracking motion during actual experiments by teleoperation. In the experiments, it can be seen that AET can successfully pass through the pipeline, which is bent with specific shapes. The main factor that contributes to the success is AET's inherent continuous motion. Being able to bend continuously enables it to adapt to the curly and narrow pipeline. Finally, we will verify the ability of AET to work in complex cluttered environments filled with obstacles. We stack several boxes, leave a vertical gap, and put an object to be grasped under one of the boxes. The whole process can be divided into 4 steps: entering the environment, navigating in the environment or avoiding obstacles, interacting with the object, and retreating to successfully pass the gap and grasp the object. The robotic arm must be flexible, otherwise, the UAV will collide with the boxes when the robotic arm reaches the magnetic object. Then, we put the object in a semi-closed box with circular holes. As the holes are small, radius of 5 centimeters, It is challenging for conventional aerial manipulators to enter the box due to their rigid links, let alone avoid obstacles to grasp the object. The experiment demonstrates that AET can successfully enter the box through the hole, avoid the obstacle, and grasp the object. Finally, the environment is more complex. This task is highly challenging as the aerial manipulator must pass through two holes on the top and right side of the transparent box, and then bend its arm to reach the object. Thanks to its dexterity and compliance, the AET can successfully accomplish the task, which fully demonstrates the extraordinary manipulation ability of AET for complex, cluttered, and constrained environments. Additionally, we perform the whole body planning for AET to autonomously execute aerial locomotion tasks. In the experiment, we establish a series of waypoints to create a sequence of alphabets. Arclab on the horizontal plane, the AET's end effector can successfully track the continuous waypoints and finish the aerial writing. Furthermore, we introduce a static ring with a diameter of 0.24 meter as a confined space. AET is tasked with tracking a planned trajectory, derived from the given waypoints, to navigate through the ring and arrive at the final position. The whole body planning method can autonomously guide AET to seamlessly traverse the ring and reach the final goal.